Hello, welcome to another module in this massive open online course. So, let us consider another digital modulation scheme, in fact, which is a very general and powerful digital modulation scheme, which is one of the most commonly used digital modulation scheme, which is used in all the modern wireless communication standards such as 3G, 4G, and also potentially in the future in 5G wireless communication standards. Alright, this is known as QAM or quadrature amplitude modulation, and to some extent is a generalization of all the schemes that we have seen before, that is your BPSK, amplitude shift keying, PAM, also so QAM is a general version of all these things. Okay, so let us start looking at quadrature. Quadrature. So, let us start looking at quadrature amplitude modulation, or this is basically this is also known as QAM, and to be a bit more precise, this is known as M-ary QAM, M-ary quadrature amplitude modulation. Basically this implies that there are M symbols, as we have seen M-ary PAM, in M-ary QAM there are M symbols. Okay. Now, similar to quadrature phase shift keying, as I said, this is a generalization of QPSK. Similar to quadrature phase shift keying, there are two pulses P1 and P2. P2T, which are orthonormal, okay, and we have xt equals A1 times P1T plus A2 times P2T. Okay. So, and now A1, now in QPSK each A1 A2 are two BPSK symbols, alright, A1 A2 element of plus or belongs to either plus or minus P. Here A1 and A2 can be two separate PAM symbols, that is the whole idea. There can be two separate PAM symbols. So, A1 and A2 are drawn from a PAM constellation independently, okay, independent symbols drawn from a PAM constellation, okay. These are independent symbols from a PAM constellation. Okay, so A1, so we have pulse P1T on which we are transmitting symbol A1, pulse P2T on which we are transmitting symbol A2. Both A1 and A2 are individual PAM symbols. So, now in quadrature phase shift keying QPSK, A1 and A2 are individual BPSK, binary phase shift keying, that is A1 is plus or minus A, A2 is plus or minus A. Here we are generalizing this concept. So, A1 can belong to a PAM, pulse amplitude modulation, A2 can belong to a PAM, and A1 and A2 are independent symbols. So, we are transmitting two PAM symbols per every waveform xt, okay, two PAM symbols for every waveform xt, okay. Now, as we have seen in QPSK, our P1T, this is similar to QPSK, that is unit energy pulses, square root of 2 over t cosine 2 pi f c t plus p2 t is square root of 2 over t sine 2 pi f c t (0 less than equal to t less than equal to t), and the t is the duration of the symbol contains an integer number of cycles, that is the same. P1 P2 T are unit energy, that is unit energy orthogonal pulses, that is a set of orthonormal pulses. This is similar to, in fact identical, in fact not even similar, this is simply identical, okay. That is, these are in quadrature, okay, to QPSK EP equals 1. Remember, this is your pulse energy. The pulse energy normalized to 1, and the bases P1 P2 T are in quadrature. P1 T P2 T are in quadrature, because remember sine 2 pi f c t plus pi by 2 root 2 over t sine 2 pi f c t plus pi by 2 equals root 2 over t cosine 2 pi f c t. So, differ by, what does it mean to say they are in quadrature? We have seen this before. Pulses P1 T P2 T differ in phase by pi by 2. Differ in P1 to P1 T P2 T differ in phase by pi by 2. Okay, so the pulses are in quadrature. Okay, and the phase difference between these pulses is pi by 2, implies they are in quadrature. Okay, now let the total number of symbols in the QAM be m. So we are saying this is an M-ary QAM, total number of symbols. So the total number of symbols, in fact the total number of symbols in this constellation is equal to m. That is why it is known as, we have said that, that is the reason it is known as M-ary QAM. M-ary QAM means total number of symbols in the QAM constellation is m, okay, which means each, now this implies that each, now this is something that you have to understand, each A1 A2 is drawn from a PAM with square root of m. This is a key observation. So, this is each A1 and A2 is drawn from a PAM, that is PAM constellation, PAM symbol set with square root of m symbols. The reason being that A1 belongs to a PAM constellation with square root of m symbols, that is A1 can be chosen in square root of m ways. A2 belongs to a PAM constellation with square root of m symbols. A2 can be chosen in square root of m ways. So, the total QAM symbol can be chosen in square root of m into square root of m, that is m ways. Okay. So, the total number of symbols in the QAM then becomes square root of m into square root of m. This is similar to QPSK. For instance, A1 is in QPSK, A1 is chosen from plus or minus a, that is a set containing 2 symbols, BPSK. A2 is chosen from a BPSK, set containing 2. So, the total number of symbols, constellation points in QPSK is 2 into 2, that is 4. Similarly, in M-ary QAM, we are choosing A1 and A2 from PAM constellation with square root of m symbols. Okay. So, therefore, what happens is total number of symbols in QAM this is equal to square root of m into square root of m, which is basically simply equal to m. Okay. Now, similar to what we have described about PAM, except now we are using square root of M-ary PAM, not M-ary PAM. Note, we are now using, so everything remains the same except M-ary PAM becomes square root. So, M-ary QAM can be thought of as comprised as being formed. So, M-ary QAM can be thought of as being formed from two independent square root of M-ary PAM constellations. Alright. So, our PAM is going to be now a square root of M-ary PAM, that is each A1 A2 belongs to a square root of M-ary PAM, that is the interesting aspect. Okay. So, A1 comma A2 belong to a square root of M-ary PAM, which means that A1 equals plus or minus 2i plus 1, 0 less than or equal to I. Remember, in M-ary PAM we have 0 less than I less than or equal to m by 2 minus 1. This will be equal to square root. So, naturally I have to replace m by square root of m. So, this will be square root of m by 2 minus 1. So, naturally, since we are considering 0 less than or equal to I less than or equal to square root of m over 2, this means that, this naturally means that, remember, naturally means you cannot choose any value of m, square root of m over 2 must be an integer. Naturally means that square root of m over 2 naturally means the square root of m over 2 must be an integer. For example, we have 64 QAM, that is m equal to 64, square root of m equal to 8, square root of m by 2 equal to 4, which is an integer. Okay. So, each PAM consists of 8 symbols. Each constituent PAM So, each constituent PAM comprises of 8 symbols in 64 QAM, and naturally total number of course we have not seen, of course it goes without saying, total number of bits per symbol in this QAM 64 QAM, total number of bits per symbol equals log to the base 2 m, that is log to the base 2 64. This is basically log 2 to the base log m to the base 2, which is basically 6, and you can see this corresponds to 3 bits per each PAM, which is 8 symbols. Log 8 to the base 2 is 3. So, 3 bits per each constituent PAM. So, the in phase component PAM, that is along P1t, carries 3 bits. PAM along the quadrature sin 2 pi f c t pulse square root of 2 over t sin 2 pi f c t carries 3 bits. Total number of bits is 6 bits per symbol in the 64 QAM. Okay. So, that is the point that we are trying to make. Okay. Now, similarly, let us complete this discussion over here. A2 is also plus or minus now 2j plus 1. Okay. A where A is, remember, A is again the same, 0 less than or equal to square root of m by 2. Now, A is similar to before, where 2a is the separation or distance between levels. Separation between levels of the PAM, successive levels of the PAM is 2a. So, A1 is plus or minus 2i plus 1a, A2 is plus or minus 2j plus 1a, and both I and j lie between 0 and square root of m over 2 minus 1. Okay, so that is the point. Now, further, if average symbol, now let us find again the value of A. Remember, we have to keep the average symbol energy constant. So, let us say average symbol energy is Es for the M-ary QAM. Alright. Now, what is the corresponding value of A? Okay. Now, let us say average symbol energy equal to Es, which implies average energy. Now, there are two QAMs, so each shares half of the energy. So, average energy per A1 equals Es by 2. Average energy per A2 equals Es by 2. So, we say each QAM, each constituent PAM has half the symbol energy, that is Es by 2. Okay. Now, again going back to our PAM, now remember we have M-ary PAM or square root of M-ary PAM. Okay, which means, and difference between levels is 2a, distance between levels is 2a. Which means average energy equals, well, a square by 3 times square root of m square minus 1. Now, remember, when we had M-ary PAM, the energy was a square over 3 times m square minus 1. However, here we have a square root of M-ary PAM, therefore, the average energy per PAM is a square, for each constituent PAM is a square over 3 times square root of m square minus 1, square root of m whole square minus square root of m square minus 1, which is basically m minus 1. Okay, and this should be equal to the average energy per PAM, which is Es over 2. So, we have Es over 2. So, this is a key step. Average energy per constituent PAM is Es over 2, and each PAM is only a square root of m PAM. So, therefore, we have this equation. Now, if you look at, if you do not remember this derivation, you can look at the derivation we have done for the M-ary PAM. There we had Es equal to square root, Es is equal to a square over 3 times m square minus 1. Here we have Es over 2 equals a square by 3 into square root of m square minus 1, which basically implies Es is equal to, well, this basically implies, or the other way around, rather As, or rather A is equal to 3 Es by 2 m minus 1, and this is an important number. So, the amplitude A, or the distance 2a is such that A for each square root of M-ary PAM, A for each square root of M-ary PAM, constituent square root of M-ary PAM is chosen as 3 Es by 2 m minus 1. So, this ensures, remember what is the constraint here, ensures average energy ES for average energy ES for M-ary, for the M-ary QAM. Okay. So, all right. So, what we have done here is basically we have introduced a different modulation which is generalized version of PAM. In fact, for that matter, generalization of several schemes, BPSK, QPSK is generalization of BPSK, PAM is a generalization of BPSK, and QAM basically is a generalization of all these such modulation schemes. So, it contains a combination of two PAMs. There are two constituent PAM constellation, pulse amplitude modulation constitution, each of containing square root of M symbols. Therefore, the QAM is M-ary. Alright. So, M-ary QAM is formed from two constituent square root M-ary PAMs, each transmitted on one is transmitted on the cosine 2 pi FCT component, other is transmitted on the sine 2 pi FCT pulse. Both of the pulses are in quadrature. So, it is quadrature amplitude modulation. Alright, previously had pulse amplitude modulation. Now, we are using two pulses which are in quadrature. So, it is quadrature amplitude modulation. Each constituent PAM is square root of M symbols. Okay. And what we have derived is basically to ensure each constituent PAM has average symbol energy ES by 2, that ensures energy ES for the M-ary QAM, and then we have derived a relation for the constant A, alright, correspond to each constituent square root M-ary PAM, such that the average symbol energy is ES for the overall QAM constellation. Okay. So, we will stop here, and in the next module we will look at what is appropriate receiver, okay, the processing at the receiver and the resulting bit error rate, symbol error rate, and also this overall symbol error rate for the QAM constellation. Okay. Thank you very much.